So what we did so far, I guess, was we had this equation, and the first thing we did was we found, or parametric equations, and the first thing we did was we found the slope of the tangent when t equals 2. Slope of the tangent, of course, goes back to your question, the slope of the tangent is dy dx. Because you're still in the xy plane, you're using t to describe the graph in this parametric equation kind of way. So to find dy dx, we just said that that's the same as dy dt over dx dt. So you calculate that, and then there you go. So that's how we find the slope of the tangent to the graph. Okay? So now, next question. Find the slope of the tangent at 1, negative 2. Well, this is tricky because what we've been saying is that the graph is determined by our value for t. Only here we're not being told the value for t. We're being told, sure, we're somewhere on the graph, but we're at the point 1, negative 2.
So
the thing is, if you want to calculate anything, you have to figure out what t is.
where we plug it in with x equation with the left side and the y
Yeah.
equation with the right side?
Exactly. Okay. So what do we know? We know that x equals 1, y equals negative 2. So we're going to have to find t. So the question is, what's t? So how can we do this? Well, yeah, you just plug it in. So we now have the equations 1 equals t squared, and in y, you get negative 2, I'll put and, negative 2 equals t cubed minus 3t. Okay. Well, right off, what does the first equation tell you? It tells you that t has to be either 1 or negative 1. So now we can just figure out which one it's supposed to be. So if t is 1, what happens in the y equation? Yeah. Then you get negative 2 equals negative 2, so that works. And let's just show that it doesn't work the other way. If t equals negative 1, then you get negative 2 equals what? You get negative 1 minus negative 3, so you would get 2. And that clearly doesn't work. So we know what t has to be. T has to be 1. And now that we know that t is 1, we can go ahead and do the problem, in a sense. Okay. So t equals 1. Well, we already have the expression. So the question was to find the slope of the tangent. We already know what dy dx is. So now we just need to plug in let's see. So remember it was 3t squared minus 3 over 2t. At t equals 1, dy dx equals 1 squared minus 3 over 2 times 1. And that just works out to be, 0. Okay. So at that point, the slope is 0. So what does the tangent look like? The tangent is horizontal. Next, confirm that there are two tangents at the point 3, 0. Now, how can there be two tangents at one point on a graph? Well, let's take a look at some of the crazier stuff. So here, every point has a single tangent line. However, what about this graph? Are there points that have more than one tangent line? Exactly. So any place where the graph crosses itself, you can think of each of those sort of parts of the path as having its own tangent line. So again, parametric equations let you have these crazy things that we've never had before. All right. So how do we do this? Well, we've got to find a way Got to find a way to describe that.
No, it would be.
So what we see is that what this means, what we're really asking, is at the point 3 comma 0, does the graph intersect itself? There should be two values of t for that point, exactly. That's the idea. So let's confirm that that's actually true. So let's see what happens. So let's see. Let's pull the equation back here. Okay. Oops. Heck is it? There we go. All right. So actually, you know what? Let me just copy over the equations. So we have x equals t squared, y equals t cubed minus 3t. Okay. Now we're back in business. Okay. So let's see if that's possible. So what we're saying is that 3 should equal t squared, and then 0 and 0 should equal t cubed minus 3t. So how many solutions are there to this?
Right side has definitely two.
Okay. So yeah, so we have to make sure that the solutions satisfy both the x or both t equations, the one that came from the x, one came from the y. So what are those two t values?
Plus or minus the square root of.
Yeah, plus or minus the square root of 3. Okay. So what we get, so on this one we have 0 equals t squared minus 3. And then on the right side, you wind up with 0 equals t times t squared minus 3. So obviously, so t equals 0 is a solution on the right, but it's not a solution on the left, so you don't need it. But all you have to satisfy is t squared minus 3, and that'll satisfy both equations. So clearly what you get is t equals plus or minus the square root of 3. So both those t values will land you at the point 3 comma 0. So now we have to figure out, okay, so if those are both those t values, so now the rest of the question was find the two slopes.
There would be basically two slopes.
Right.
So does that mean that as long as the curve, our path is smooth and continuous, dependent on how many solutions of t we're gonna have, that's how many slopes we're gonna have there, tangent lines. Sorry.
Yes.
Okay.
Now, I mean, of course, it's possible if a graph keeps coming back to itself, it's possible that it comes in at exactly the same slope. So it could be that your new tangent line is the same as your old tangent line. You simply just have to calculate it and see what you have. So let's calculate it and see what we have. So at t equals positive root 3, the slope equals 3 rad 3 squared minus 3 over 2 root 3. So what does that work out to? 6 over 2 root 3, or in other words, 3 over root 3. Or if you like, 1 over root 3. Excuse me, rather, that's just root 3. Okay? Now let's check it out the other way. What about t equals negative root 3? Now we get dy dx equals 3 negative root 3 squared minus 3 over 2 times negative root 3. So you should see immediately how this is going to work out. It's the exact same thing, except there's a negative in the denominator. So there you go. So you can graph it, and it looks like this. And what you can see, make this a little bigger. So you can actually see which point we're at. We are at this point right there. That's the point 3 comma 0. And you can not as a proof, but you can see it looks pretty clearly that the graph comes in, crosses to that point one time, then crosses through it again. So it comes to that the path comes through that point exactly 2 times. One of them has a positive slope, one of them has a negative slope, and we just calculate what that actual slope is.
Just
Okay, so let's. Okay, so that's how we can talk about 2 different tangents at the same point, which previously was a crazy idea. But with parametric equations, we can do lots of new things we couldn't do before. Okay, so find the points where the tangent is horizontal and where it's vertical. Well, like we said, we actually already found one of those because we got where t equals 0. Where t equals 1, the derivative was 0. Let's see if that happens any other times. So, let's take a look. So for horizontal, we want dy dx equal to 0. So 3t squared minus 3 over 2t equals 0. Okay? So now we have to solve that. So how do we solve that out? Just algebra. Cross multiply. You get 3t squared minus 3 equals 0. Divide by 3. You get t squared minus 1 equals 0. You can do this properly by factoring, but I think it's quite clear. You get t equals plus minus 1. So we'd actually, by accident, in part B, discovered at t equals 1 that we have a horizontal tangent. And now we know that also at t equals negative 1, we have a horizontal tangent. Okay. So to have a vertical tangent, what should dy dx be equal to? It should be like undefined or infinity, something like that. dne infinity, something like that, right? So we have 3. So, actually, yeah. So what equation does that give us? That just gives us 2t equals 0. So t equals 0.
Does it matter what the result is in the numerator? Does it matter like?
Okay. So it's true. We should check. At t equals 0, we get 3 0 squared minus 3 over 2 0. So that's just negative 3 over 0. So that is undefined. That does give you a vertical tangent. Okay. Okay. So now let's go back and look at the graph and try to figure out where these points are. So we can look at it and we can see immediately. Okay. So you can tell just from looking at the graph that right over here and right over here we have the horizontal tangents. Now I'm not sure which one is positive 1 and which one is negative 1 unless I think about it for a second. But since x is t squared and y is t cubed, probably as t gets bigger, x and y are getting bigger, so it's probably going in this direction. So that would give me that t equals 1 over here and t equals negative 1 over there. And where is the vertical tangent line? It's right over there, and that's where t equals 0.
We do this graphically. We do it with the same graph, but we can.
So yeah, so I'm showing you this so that the idea is that you can either think of this algebraically or you can think of it graphically, and of course the two should agree. And then finally, let's answer the last question, which is to find the second derivative. So in this case, the way we find a second derivative, you have to think of it as finding the derivative of the first derivative. Okay? Now that sounds pretty obvious, but it's a little trickier because we're dealing with parametric equations. So remember what we discovered about finding the second derivative. What you do is you first you find the first derivative, which is someone that we already did, and then you do d dx of that, which means do the exact same process. Do d dt of that thing over dx dt. So what does that look like in this calculation? What does that mean? So it means d dt dx dt over dx dt. So what was dy dx? dy dx was 3t squared minus 3 over 2t. And now we want to take the derivative of that with respect to t, which now, thank God, we're all in t, so we can just put a little prime there. Okay. Over dx dt. Well, what was dx dt? We already found that. That was 2t. So now I've got to work this whole thing out. So how do you find the derivative of that thing? It's just the quotient rule. So it's d this minus this d this. Now it's going to be over 2t squared, and then the entire thing over 2t.
What's funny because I think it's easier if you just break this thing up or
But then
you could just break this up 3t2 squared over 2t. Negative 3t.
We have to use the quotient rule because we're taking the derivative of a quotient, so we have to do it in that way.
Take the derivative, simple.
Okay. So let's keep going with this long way. So this winds up being 6t times 2t minus 2 times 3t squared minus 3 all over. So notice that over 2t squared over 2t is really just going to be over 2t cubed. So now we can simplify this. 12t squared minus 6t squared plus 6 over 8t cubed. And then that's just 6t squared plus 6 over 8t cubed. And I guess we can finally cancel another 2. So you get 3t squared plus 3 over 4t cubed. So yes, it's true. You could have simplified this expression first because it's just everything over 2t before you took the derivative. So we could have found the derivative in one or two steps like that. Okay. And now it sort of seems to make more sense to break it up, and then this would be 3/4 t to the negative 1 plus 3/4 t to the negative 3. Which is what you get if you rewrite our original thing as well. So of course, keeping it as one fraction or breaking it up into two fractions, same thing. Different way of writing the answer. Okay. So there's often more than one way to sort of handle the algebra when you do calculations like this. So anything that's correct is fine. Okay, next, calculating area. Well, so previously what we saw is that you can find area just by doing a simple integral. So usually we've written it as y equals f of x dx, but I think for obvious reasons I'm going to write that as integral y dx. Because we no longer have y equals f of x, we only have y. So the integral of y dx gives you the area. Well now, we don't want to write dx because our variable is not x anymore. We want to rewrite everything in terms of our variable being t. So how do we do that? Well, by simply thinking of x as a function of t, you use like a chain rule or like a use substitution type substitution. And you simply write dx is dx dt times dt. Or if you like, x prime times dt. So you just make that substitution, and now everything's correct. And you can use it. So I hope everyone recalls when we talk about substitution, remember like writing, say like your x variable as a function of another variable, and then figuring out what is dx. And dx winds up being like x prime times dt, or something like that. From integration. Okay. Okay. So we can use this to calculate areas of these nice things. So for example, we have this set of parametric equations. Now I'm going to tell you what defines an ellipse, but let me show you. So when you graph it out, there's your ellipse. So notice that we're, in a sense, where do ellipses in our development come from? Well, if x was just cos t and y was sin t, you just have a circle. But throwing those coefficients in there sort of stretches the circle. It stretches the circle, for example, by making the x values slightly bigger, by putting the 4 in front as opposed to y values where there's just the 3 in front. So stretching out the x values means you sort of got a circle but stretched in the x-axis direction. And that's an ellipse. Yeah, okay. So how do we do it? Area equals the integral of y dx dt. Okay? Well, now let's apply it to our particular situation. It's the integral, so y is 3 sine t times dx dt.
-4 sin t.
It's -4 sine t dt. And now, of course, we need the boundaries of integration. So what do you think the boundaries of integration should be? From 0 to 2 pi, because 0 to 2 pi will pass us around the ellipse exactly one time. There you go. Let's see. Except we have to be careful, because what happens if we do that?
It's sine squared t.
Well, let's think about what area means. So, yeah, we're gonna get 0. Okay. So yeah, so think about what we've done. We're taking remember this is equivalent to y dx. So we're taking these areas. So remember the way the graph goes is like t is like your angle. So you're going from here to here to here to here. So you're taking all these areas, all these areas, all these areas, all these y values, and then you're taking these y values and these y values and these y values. So if you do the integral from 0 to 2 pi, what are you going to get? You're going to get 0. So what should we do in order to find the area?
Take it into pi multiplied by 2.
Integral from 0 to pi and multiply by 2. Or we could even go from 0 to pi over 2 and multiply by 4 because we know about the symmetry of an ellipse. So either way. Okay. So let's just do this one. From 0 to pi, and then we're going to multiply by 2. Okay. So now we have, so if we rewrite this, so we can actually do better than just that. We can pull out the oops, not what I meant to do. Hold on. Okay. So let's rewrite this. So we know we're going to have sine squared dt in here, and then we're going to have a negative 24 on the outside. And we know how to do this integral. Now we just have to go do it. Or I should say, this technique you've learned previously.
We write sine squared as well.
Power series.
Cosine 2a.
Oh, now that's over 2. Okay. Let's see. So the integral of 1 minus cos 2t dt. Okay, so in brief, I could do a u sub on the 2t, but I really know that's just going to make a 1/2 pop out, so I'm just going to do it in my head. So the integral of 1 is going to give me a t, and then the integral of let's see, the integral of cosine is going to give me negative cosine, going to give me negative sine 2t, but over 2. Okay, so then you evaluate this at pi and 0. Now it's nice because sine of pi and sine of, or even when you multiply by 2, so sine of, it's going to be sine of 2 pi, that's going to give you 0. Then you plug in 0, sine of 0 will give you 0. So that part just goes away. And then you wind up with negative 12 pi. Now I'm going to go back and fix why that should be positive instead of negative. You have to trust me. Okay, so there's the area of your ellipse, is 12 pi. Now, does anybody want to venture a guess as to what the general formula for the area of an ellipse is? Look at the equation that we started with, and look at what we finished with.
It's 4 cos t plus 3 sin t equals 2 12 pi.
Well, we started with x equals 4 cos t and y equals 3 sin t, and we got, as a result, 12 pi. So where do you think the 12 part came from? 4 times 3. Exactly. So now that's something that you could actually prove if you wanted. So in fact, it's clear that 3 and that 4 simply come out as factors. So they sit there, and then the 2 winds up canceling. So in fact, we now know the formula for the area of an ellipse.
So the area of an ellipse, which is
The factor is multiplied times pi.
yeah.
For an ellipse where x equals a cos t, y equals b sine t, the area equals pi times a times b. And in fact, I just want to show you that we actually just proved the area of a circle. Because what is a circle? It's an ellipse, but where a and b are the same. And when a and b are the same, what do we usually call that on a circle? That's the radius.
How about the pi though?
So what's the area of a circle? Pi r squared.
Oh, that's so beautiful, man. They should have told me that in third grade. In third grade, they should have told me that.
Next. So we just proved one really cool general theorem in math. Let's go do something else. Calculating arc length. So how does arc length work? Well, recall what you had in just good old xy notation. The arc length, which we can denote as L, is the integral from a to b of the square root of 1 plus the derivative, which was dy dx squared, square root of that whole thing, and then dx. Okay. Well, once again, we're going to have to turn this using a substitution, or turn it around to use the, t as our variable. So the way we're going to do this is we're going to go back to how we actually derived the formula for arc length. So if you recall, the formula from arc length came from the Pythagorean theorem. Pythagorean theorem said it was like delta x squared plus delta y squared is like the side squared, and then you add all those up, and then adding them all up becomes a rectangle. So, and then at some point you did a manipulation by pulling out the dx and dividing by dx. So you used dx over dx in your calculation because you knew you wanted a dx because dx was your variable. But now we're going to do the exact same thing, but our variable is not x. Our variable is t. So let's go back and take a look. So one quick comment. In upper mathematics, typically arc length or lengths are represented by s. I don't know why. Maybe it's some Latin thing. I couldn't say. All right. So ds. So s is your arc length. So again, if you think on a very small scale, a short piece of your graph is approximately linear. So we have this idea that dx, which is the horizontal change, and then dy, which is the vertical change, and then ds is like your hypotenuse. So ds squared equals dx squared plus dy squared. So now instead of dividing by dx, or instead of having dx over dx, we're going to have dt over dt. So in this case, we're going to divide by, because we haven't yet taken the square root, so it's dt squared over dt squared. And now we take the square root. Okay. So notice, so basically now we're at, and then when we integrate, we get the formula that we want. So the integral of ds, is the integral of a small change in s, is just s itself, is the arc length. So let's compare this to our original formula. Okay. So first of all, let me say that, notice that our variable again is dt. So when you write boundaries of integration, those are t values. Okay. But another comment, we talked before about if you're in parametric equation form, sometimes, or actually, you can go back and forth between xy equation form and parametric equation form. So what if we were to go from here into xy form? So what if we simply said we had a graph where y was actually a function of x? Then the way that you would write that down, as we said, is by simply saying x equals t, and then y is a function of t. So what if we made the x equals t substitution here? What would happen? Well, what do you get? You get dx over dx squared plus dy dx squared. But dx dx is just 1. In other words, you would get this if you simply say that y equals t. Excuse me, if you simply say that x equals t. So once again, the parametric form is the generalization of the xy notation. Okay. So let's use this. Let's find the circumference of a circle. Let's actually prove it using calculus. Oops. Okay. So the first thing is I'm telling you a circle with a radius r equals 3. So first thing we have to do is we have to write down what is the equation of a circle. So if we were just doing this in xy notation, we'd say x squared plus y squared equals 3 squared, and then we'd want to be integrating, we'd have to take a derivative of something with a square root, and then algebraically that would be messy. Let's see what happens when we use parametric notation. So first of all, this would be the equation of a... So we've already seen that x equals cos t and y equals sine t is the equation of a circle. That circle, of course, had radius 1. What do we do if we want to make it radius 3? You simply multiply all your values by 3. Your circle is 3 times as big. The radius is now 3. So first, I hope that makes sense. So there's the equation for a circle with radius 3. Great. Next, now let's actually find the value for this thing. Okay, let's do it. So I'm going to write S, but you could equivalently write L for length or circumference. So this should be the integral of the square root of, let's see. So dx dt squared plus dy dt squared dt. And now we got to set this up. So first of all, when we take this integral, the integral should go from what value to what value?
2 pi, 0 to pi.
Right. So in this case, we do want to go from 0 to 2 pi. How come? Because we want the arc length for the trip that goes exactly once around the circle. So that's 0 to 2 pi. Okay? Now, square root of, so what is dx dt? Well, x is 3 cos t, so the derivative is just negative 3 sine t. And we're going to square it. Y is 3 sine t, the derivative is 3 cos t. So I want 3 cos t, and I'm going to square it. And dt. Okay. So now we need to simplify that. So the first one, you get 9 sine squared t. The second one, you get 9 cos squared t.
So we take 9 out, sine squared t plus
You pull out the 9, exactly. So you get the square root of 9 times the square root of sine squared plus cos squared. Oh, oops. Oh, come on. All right. And in one step, magic. It's just 1. And boy, that integral could not be easier. And so from that, can you see what the general formula is going to be for the circumference of a circle? Yeah. Because the 3 just came from the r. It was 3 squared, and then we took the square root. So in general, it's just 2 pi times r. So we just proved the circumference of a circle. Surface area. Surface area comes along nicely because Previously, we saw the formula for surface area from revolving y equals fx around the x-axis was this expression. So I like to write it in the shorthand that it's 2 pi h times L, where L is your length, and then h is the height of the thing that you're revolving. I think sometimes I use r as the radius of the thing that you're revolving, either way. Okay. So that just becomes 2 pi times the integral of y, and then that whole thing, which is really that's just your expression for arc length. But now we know what to do with that. For parametric curves, it just becomes this. 2 pi times the integral of y times the square root of dx dt squared plus dy dt squared. So extending it to parametric curves is very straightforward.
Wait, H and L, they're two.
So let's do a nice example. Let's find the surface area of a sphere with radius 3. So where does that come from? Well, we just had a circle of radius 3, and we used that to make a sphere by rotating it around the x-axis. So once again, we know that our equations are x equals 3 cos t, y equals 3 sine t. Oops. And we rotate it around the axis, and that gives us a sphere. Now, of course, we're running into the problem here where it's hard to draw three-dimensional objects on a two-dimensional sheet. That's going to be a continuing issue in this class. Okay. So let's find the surface area. So surface area equals 2 pi integral y square root dx dt squared plus dy dt squared dt. So what does that give us here? So it's 2 pi times the integral. Now we want to go from what value to what value regarding t?
Pi to 2 pi.
Do we want to go from pi to 2 pi?
Zero.
From 0 to 1 pi.
We want to go from 0 to pi. Because going from 0 to pi takes us from here to here, and that's the part of the graph that we need that we spin around the axis in order to make it a sphere. Okay. So we need that. Now we need y. So y is 3 sine t. Now we need the square root of. We have the exact same expression that we had before. So, I'm going to write it down. We know this winds up being negative 3 sine t squared plus 3 cos t squared, and that's all going to be dt. But again, as we saw last time, all that simplifies in beautiful fashion. And this just winds up being 2 pi, the integral from 0 to pi of 3 sine t times, that whole thing just winds up being 3. Okay. So the integral of sine is negative cosine. So we've got 18 pi negative cosine t from 0 to pi. So we plug in pi, and cosine of pi is negative 1. So that's going to give us 18 pi, and then minus. When you plug in 0, what do you get? Yeah, cosine of 0 is 1. Don't always assume that plugging in 0 gives you 0. Big mistake, right? So you plug in 0, you get cosine of 0 is 1. So that gives you negative 18 pi. So you add them together, you get 36 pi.
Can you explain not equal from 0 to pi? 'Cause nobody wants-
So you can pick out from here the general formula for the surface area. There's a radius, there's a radius, there's a 2, there's the pi, and from over here you can see that it doubles, that gives you another 2.
General surface
So
area-
stick it all together, you get 4 pi r squared.
General surface area for a sphere.
Surface area for a sphere, of course, sure. Not for any possible mathematical object.